All right, ladies and gentlemen.
No, we're going to take a pause on induction. We're going to take a pause. What's that? Oh, yeah. I mean, we're not done with induction, but I want us to not get mired down with it. I want us to get some things knocked out and under control. I don't want you guys waiting in the window. So we're going to move. We're going to come back to induction, believe me. We're going to see it throughout. Okay, and we're going to use it as a tool to prove things from down the road. But this is all right. Today we will study, or begin, almost imaginary numbers. It's cool. No, actually, if anybody's interested, there is a very interesting history to complex numbers. And if anybody's interested in a really cool IA, looking at complex numbers, their history, what they're used for, their real-life practical applications of them, and things like that, is a really cool topic. Yeah.
You got like you're making pyramids. It's why I was trying to figure out. You got constant numbers. Please assume that it's not possible.
Well, a lot of mathematics has gone through a very interesting history. And if you're interested in the history of mathematics, I have some excellent books that talk about different parts of the history. Why was 0 and infinity banned numbers? Why did some people not believe that there were such things as negative numbers for a long time? Mathematics has evolved. It wasn't just dropped on our lap. It didn't come down from the mountain. All right. So imaginary complex.
People don't believe in 0.
Yeah, people didn't believe in 0 for a very long time. Now, if we look at this set, we can, ladies and gentlemen, we can partition the real numbers, the complex numbers, into two parts. Okay. Well, I shouldn't say that. The imaginary numbers, pure imaginary numbers, have no real part. So let's be clear about this first. A complex number is of the form a plus ib, or bi, where a and b are elements of the reals. All right, where I is defined as the square root of -1, or more specifically, the solution to x squared plus 1 equals 0. Okay, that's where we get I. All right. The pure imaginary numbers have no real part. So the A is my real part. And this is the imaginary part. Sometimes you see the real part abbreviated as just RE, and this part as IM. Okay. Sometimes you'll see that in books, or the instructions to a problem, or sometimes even in programming languages, and in and as an operator on a calculator. From time to time, you'll see those things as well. So those are your basic definitions. Okay. Now, imaginary numbers are fun, and we're going to play with them. We played with them in Algebra 2, and we're going to kind of spend today rehashing those rules and talking about what the geometric idea behind a complex number is. Okay. So I want you to to understand the difference between a complex number and an imaginary number. A complex number has a real part and an imaginary part. And an imaginary number doesn't have that real piece. Okay? Does that make sense? All right. So, first and foremost, what is an imaginary number? There's a graph, a very interesting graph. It's called an Argand diagram. And in an Argand diagram, we get a geometric idea of what this means. So, for example, if we think about the real plane, the coordinate plane that you have been graphing your lines on, an XY plane. It looks we have something that looks. You have seen this since you were in kindergarten, right? Sure, we played with complex numbers, the coordinate plane in kindergarten. But the imaginary numbers are not real numbers, okay? So we have to figure out a way, where would we put them? Well, what we do is we create another axis. This one coming out of the plane, okay? And that axis we can now use to define another plane. See what's wrong? Now, we aren't interested in the real plane right now. We're interested in the imaginary plane. So what we're going to do is we're going to tip this thing. We're going to rotate it upward. Because we really want to look at this plane. This is the plane we're interested in. Because this is my imaginary plane. So let's rotate it upward. Okay? And what we wind up getting is a regular looking plane again. But now, this axis is the real axis. And this axis is the imaginary axis. All right. So, you could think about this as an XY plane. And if I had a point, let's say 5 plus 2i, okay, if this is a point now, we can think about it as having 5 real parts, 5 real units, and 2 imaginary units. Okay? This is 1 plus 1 plus 1 plus 1 plus 1, right? Plus I plus I. If you think about it that way. Okay? So this would be the point 1, 2, 3, 4, 5, 1, 2. if we were to draw it on an imaginary plane. All right? And we represent it not just with a point oftentimes, but instead with a vector. Okay? And a vector to that point. Right? So let's think about, for example, for a moment, what is a vector? Okay, because we haven't talked about vectors specifically, but who here is taking or did take physics? One. Okay. You did? Oh, you did too? Oh, okay. All right. Well, you don't have to catch up on this part. But a vector is, in a sense, you can think about it as a force. It has two parts. It has a direction and it has a size. So, for example, if I say I live 2 miles away, you don't know where I live. I could live anywhere on the circle of radius 2 miles. But if I said I live 2 miles north, you would know not only how far away, but what direction to go in. Okay. If I said if I say 2 cows, that's just a number. But if I say I got 2 cows or I lost 2 cows, that means I have a magnitude 2 and a direction, gaining it or losing it, positive or negative. All right? So you can think about moving along a number line a certain amount. Like if I add 5 or if I take away 5, I'm either going right 5 or I'm going back 5. Magnitude and direction. Here, this is saying I'm going 5 in the real direction and 2 in the imaginary direction. All right? And what we are interested in is how big is this number? Okay, if we think about a number line, we have a concept of size on a number line, right? If I talk about 5, that's 1, 2, 3, 4, 5. Now, it has a specific size. So when we talk about -5 also, it has the same size, but it has a different direction. Okay? +5 and -5 are both the same size, but they're not in the same direction. Does that make sense? This is where we get the idea of absolute value. Absolute value really is saying how big is the number. How far away is it from 0? I don't care what direction it's going in. I just care how big it is. All right? Like if I say, I need everybody that is within 5 years of my age. They could be 5 years older or 5 years younger. It doesn't matter. All I need is the group of people within a set that is above or below 5. So that's where we get this operator. The operation of absolute value means magnitude, size. All right? Now, no, it's not size. Yes, but good job. So here, if I wanted to know the size of this, this is not as simple now as counting along a number line. We need to find the length of that diagonal ray, that vector. How do you think we do it? Okay, the Pythagorean theorem. Well done. Because this is really a triangle where 5 units in one direction and 2 units in the other direction. And now we can do the Pythagorean theorem and come up with the square root of 29, which is like 5.4-ish. Somebody want to find that? You got a calculator here? Hmm?
Well, what did you get?
Yes.
5.2, you said? 5.3? Ish.
Okay. So this is still, this is a length, okay? This is a magnitude. It's how big is it, all right? And that's how you take what's called the modulus, okay? The modulus is the size of the number. You're basically taking, you're doing the Pythagorean theorem on this imaginary number in the imaginary plane. All right. Oftentimes, we will see an imaginary number written as a single variable. And that variable is often z.
Not pretty complex.
Okay, so we can sometimes say, you know, if we were talking about, we can talk about all sorts of funny things inside the imaginary plane. We can graph a polynomial in the complex plane. Okay. Well, you could have a polynomial like this. Ooh. Okay. And we can play around with all of these things.
We'll get into lots of stuff.
Complex analysis is awesome. So, how do we play with these things? So, we now have another set of numbers that we have to set up a set of rules for. Okay? So, let's learn how to add, subtract, multiply, and divide this new set of numbers.
Here's how it's done.
So, Z1 and Z2 are complex numbers. The real parts add with the real parts, and the imaginary parts add with imaginary parts. Keep everybody together. So, for example, this is not unlike normal everyday addition, except you have to keep the real parts and the imaginary parts separate. And we wind up getting
-3 minus 3 on it.
so 2 minus 5 and 3 minus 6 on it. 3 minus 6. Not very interesting, but important. Okay, not very exciting. Subtraction would be the same. But you must remember to distribute the negative sign. That's 2. I almost always try to put the bar through my keys. Just because I do know that they can be easily confused. Okay. Are we straight? So that's how to add and subtract. Nothing very earth-shattering about it. Multiplication is a little bit more interesting. Oh, sorry. So these two went together, and those two. No problem. Keep the reals with the reals and the imaginaries with the imaginaries. Sweet. You good? All right. Awesome. Next. Multiplying. So, let's do an example. Okay, you guys remember some stuff about imaginary numbers, right? From last year, yeah? Okay. Well, here, you just FOIL it out. You do the double distribution. So I get -2 plus 3i plus 8i minus 12i squared. Because it's I times I.
-1.
We'll get there. Now, I squared, this is -1 squared. I'm sorry, square root of -1 squared. So this is -1 times -1, right? Drink water. Very fast. So this just becomes -1. And we wind up getting -2 plus 11i.
Why is it -1?
Right, if I square root, if you think about what I is just the square root of -1. So you're squaring a square root, which knocks out the square root. And now, so you don't have to always go through all that gory detail, but that's really what's happening. Hold on. I have a question. Sorry.
I have no idea. But I think I've watched the news twice at 4 years.
I can't answer that question. I wasn't here to answer it for you. So you would have asked the same question. So, does everyone feel okay about multiplying complex numbers? Yes? Let's try one on your own. You can do this on boards. You can do this on paper. You're going to go to the board anyway. Yes.
Walk out like you don't like do it. Can't move.
All right, good. So I'm just for you guys to take a seat for a minute because we're going to come back to the boards in a little while anyway. So this becomes 20 plus, plus 28i minus 15i minus 21i squared goes to -1, and we get 20 plus 13i plus 21 gives me 41 plus 13i. Wonderful. Yay, math. Okay. All right. Now, we know how to multiply. Let's divide. All right. Okay. Now, to introduce a term, Let's go for a moment to the complex plane, to our Argand diagram. All right, if 2 plus I is right here, okay, over 2 up 1, yes? There is what is called a complex conjugate. And it is written, so the complex conjugate of a complex number z. So let z be a complex number. Okay. Z star. Okay. And it is located right there. This is Z. This is Z star. Okay. So from that picture, what would its complex conjugate be for 2 plus I? What would its complex conjugate be? 2 minus I. Okay, it's still the same real part. I've gone left and right the same amount, but it's the reflection of the point over the x-axis. So what we're going to do to get that imaginary piece out of the denominator is multiply by 1. You don't want to change the size of this number. It is a number. It's some weird number. But we don't want to make it bigger or smaller, so all we're really going to do is multiply by 1. It's a weird looking 1, but it's still 1. So it's the complex conjugate of the denominator. And now we have just another set of multiplications that just like we did a minute before. So we started with a complex number, and watch out, shit's about to get real. And we get 6 minus 3i minus 10i plus 5i squared all over 4 minus 2i plus 2i minus I squared. Now, right off the bat, those two middle terms are going to go away. And we can simplify these fellows. And we wind up with 6 minus 13i minus 5 all over 4 plus 1, giving me 1 minus 13i all over 5. And now we have a purely real denominator. And, you know, what's interesting is that complex numbers really allow you to do some really crazy stuff. Because if you look at the original problem, 3, 5, 2, and 1 were the numbers that I started with in here. And when we ended up with 13, and there were no factors of 13 anywhere. I mean, we wound up with 1, a 13, and a 5. We started with a 5 in the numerator, but now we have 5 in the denominator. So complex numbers allow you to do some pretty crazy stuff. Yes, mathematics. Do this one on your own or on boards.
Plus 19i over 34.
Yeah. Now let's just multiply the whole thing out, shall we? We're going to multiply by the complex conjugate. And now we FOIL everywhere, and you get 6 plus 10i minus plus 9i plus 15i squared. And we get 9 and minus 25 squared. And in fact, I can show that step. So we get plus 15i minus 15i minus 25i squared. Yes, they do. And the reason why they always cancel goes back to the when we talk about the difference of squares. Okay? If you look carefully at this and that, they look a lot like right? Remember the difference of squares? And they, or, you know, right? And when you did this, you remember that your two middle terms cancel out. And you wind up with, you know, x squared minus 16. Okay? The square of both parts. So this thing simplifies nicely. And now we have, and we wind up getting 6 minus 15 plus 19i all over 9 plus 25, which gives me negative 9 plus 19i all over 34. Now, it is important to note that sometimes you can pull out a GCD from your numerator and simplify a little bit. Okay? So, for example, not in this problem, and I don't want to artificially create one that does, but your multiplications could yield you something like after you've multiplied everything and you've gotten your denominator to be a real thing, look for GCDs, because if you have a GCD, you should factor it and cancel it. All right? So please watch that. All right? That's the death by 1,000 cuts. You know, the 1 or 2 little points here or there to take an A down to a B. You know, little pieces. All right, and finally, last but not least, if you have only this, where there's no real part to fool with, this becomes very simple. Just multiply by I over I. Right? Because the I times the I gives me a negative 1, which makes it a positive 3. And now we just have 5 times negative 1. So I'll show the set. I'll show that set too. Okay. Yeah. It does in the next step.
You can't think of it.
Huh?
I mean, that is probably it.
Yeah, it's just normal to put the negative sign at the top. Right? Do you see? Eric? Yeah, you're good. Okay. All right. So this is how it's played. You guys are going to do some exercises on the boards. When you've gotten your answers, write your answers in pencil on here. When you've got your answer, you've got your answers, bring them up to me. I'll check them, and we'll go back and forth. We did this once or twice before, right? Yeah. A little bit of just daily practice. That's all. All right, cool. And this episode of the Rocco Show has been brought to you by our studio audience and the complex number. Oh, shout out to the complex conjugates and all of us. All right, wonderful.